Hi everyone, welcome to Comrades College of Engineering and Technology YouTube channel. In this video, we are going to discuss evaluation of complex integrals. So first let us define residues, then residue theorem, then using residue theorem let us evaluate some integrals. Now first define residues. If z is equal to a is a pole of order 1 for f of z, that is simple pole, then residue of f of z at z is equal to a, that is equal to limit z tends to a of z minus a into f of z. If z is equal to a is a pole of order m for f of z, then residue of f of z at z is equal to a, that is equal to 1 divided by m minus 1 factorial limit z tends to a of d power m minus 1 divided by dz power m minus 1 z minus a whole power m into f of z. When we substituting m is equal to 2, we get z is equal to a is a pole of order 2. Now let us see Cauchy's residue theorem. If f of z is an analytic and on a simple closed curve C except at a finite number of singular points z1, z2, etc., zn lying inside the circle C, then integral over C f of z dz, that is equal to 2 pi I into sum of the residues. Now let us see one problem using Cauchy's residue theorem. Evaluate integral over C 2z minus 1 divided by z into z plus 1 into z minus 3 dz, where C is the circle modulus z is equal to 2. Now consider here f of z as the integrand 2z minus 1 divided by z into z plus 1 into z minus 3. Here first let us find the poles. Poles are the values of z in which the denominator is equal to 0. Therefore, the poles are z is equal to 0, z is equal to minus 1 and z is equal to 3. All are simple poles. Now, here given that the circle equation is modulus z is equal to 2. Now, let us find what are all the poles lying inside the circle modulus z is equal to 2. Now, here z is equal to 0, put z is equal to 0 in the circle equation, 0 is less than 2, therefore 0 lies inside the circle. When we substituting z is equal to minus 1 modulus of minus 1 is 1, 1 is less than 2, therefore minus 1 also lies inside the circle C. Now, another pole z is equal to 3, put z is equal to 3 in this circle, modulus 3 which is equal to 3 which is greater than 2, therefore z is equal to 3 lies outside the circle C. Now let us find the residue inside the pole. So here residue R1 as residue of f of z at z is equal to 0. Here z is equal to 0 is a simple pole, therefore the formula is limit z tends to 0 of z minus 0 into f of z, that is equal to, now substituting f of z here, 2z minus 1 divided by z into z plus 1 into z minus 3, cancelling this z, then substituting z is equal to 0, we get minus 1 divided by 1 into minus 3, that is equal to 1 by 3. Therefore, residue for the function f of z at z is equal to 0, that is equal to 1 by 3. Now let us find the residue for the function f of z at z is equal to minus 1. Now limit z tends to minus 1 of z plus 1 into f of z. Now substituting f of z value here, cancelling z plus 1 with z plus 1, we get the value as putting z is equal to minus 1. The answer is 2 into minus 1 divided by like this. After simplification we get minus 3 divided by 4. Therefore, residue at z is equal to minus 1 is given by minus 3 divided by 4. Now by using Cauchy's residue theorem, the value of the integral is equal to 2 pi I into sum of the residues R1 and R2. Therefore, already we have calculated R1 as 1 by 3 and R2 as minus 3 by 4. Substituting here and simplifying, we get the answer as minus 5 into pi I divided by 6. Now, let us see another problem. Evaluate integral over C cos pi z square plus sin pi z square divided by z plus 1 into z plus 2 dz using Cauchy's residue theorem, where C is the circle modulus z is equal to 3. Now, here f of z is equal to cos pi z square plus sin pi z square divided by z plus 1 into z plus 2. Now, let us find the poles for the function f of z. Here the poles are given by the denominator f of z is equal to 0 for the value of z. Here z plus 1 into z plus 2 is equal to 0 means z is equal to minus 1 and z is equal to minus 2 are the poles of order 1. Now, compute what are all the poles lying inside the circle modulus z is equal to 3. When we substituting z is equal to minus 1, modulus minus 1 is 1. So, 1 is less than 3, therefore, z is equal to minus 1 lies inside the circle. When we substituting z is equal to minus 2, modulus of minus 2 is 2, 2 is less than 3, therefore, 2 lies inside the circle. Therefore, both the poles z is equal to minus 1 and z is equal to minus 2 lies inside the circle C. Now, let us compute the residue for both the poles. R1 is equal to residue of f of z at z is equal to minus 1, that is equal to limit z tends to minus 1 of z plus 1 into f of z. Now, substituting f of z, that is cos pi z square plus sin pi z square divided by z plus 1 into z plus 2, cancelling z plus 1 and z plus 1 and substituting z is equal to minus 1, we get cos of pi plus sin pi divided by minus 1 plus 2, that is 1. Therefore, we get R1, that is residue is equal to minus 1. Now, let us find the residue for f of z at z is equal to minus 2, that is equal to limit z tends to minus 2 of z plus 2 into f of z, that is equal to z plus 2 into cos pi z square plus sin pi z square divided by z plus 1 into z plus 2, cancelling z plus 2 and substituting z is equal to minus 2, we get limit z tends to minus 2 of cos pi z square plus sin pi z square divided by z plus 1, that is equal to cos pi into minus 2 the whole square plus sin pi into minus 2 the whole square divided by z plus 1. Put z is equal to minus 2 means denominator minus 1, cos pi is minus 1, so cos 4 pi, that is cos pi into 4, that is cos of 4 pi, sin pi into 4 sin 4 pi, cos 4 pi plus sin 4 pi divided by z plus 1, cos 4 pi value as 1, sin 4 pi value as 0. Therefore, denominator is minus 1, totally the answer is equal to minus 1. Therefore, residue for the function f of z at z is equal to minus 2, that is equal to minus 1. Therefore, by using Cauchy's residue theorem, the value of the integral, that is equal to integral over C cos pi z square plus sin pi z square divided by z plus 1 into z plus 2 dz, that is equal to 2 pi I into sum of the residues R1 and R2, that is equal to 2 pi I. Already we have calculated R1 as minus 1, R2 as minus 1, therefore 2 pi I into minus 2, that is equal to minus 4 pi I. Thank you.